So let's begin our fourth lecture. Thanks for joining me today. So let me begin with a brief recap of where we were at the end of yesterday. So what we were doing yesterday was we were trying to understand we were in the middle of developing the theoretical description of a Bose-Einstein condensate at temperature equal to 0. The main idea there was that we could basically do what's called this Bogoliubov ansatz, where we can write the field operator corresponding to the atoms in a Bose-Einstein condensate as basically a classical or mean field part plus quantum fluctuations. And at temperature 0, we can essentially ignore the quantum part completely and develop a theory for just the mean field part. This mean field part, we can understand it in many ways. One way is to understand that the many body wave function corresponding to such a mean field state is basically every atom in the Bose-Einstein condensate occupying the exact same single particle state. Okay, and with this in mind, using the evolution equation for the field operator, we were able to write down the evolution equation for the mean field, or what we have been calling the condensate wave function, right? So this object is our condensate wave function. And now from that, we developed basically an time evolution equation, including interactions, which were modeled as S wave or contact interactions, because they were of the form delta of r minus r dash. So with that, we wrote down the evolution equation, which was called the Gross-Pitaevskii equation for the mean field or the condensate wave function. It had the form very similar to a Schrodinger equation, except for this very interesting linear part, non-linear part. So it is a non-linear Schrodinger equation. And U0 here is given by this expression, and A here is the scattering length corresponding to the interaction between the atoms in this condensate. Okay, so this is the time-dependent Gross-Pitaevskii equation that we developed, and we also understood when is this applicable. It is applicable at 0 temperature, and also if the gas has to be very dilute, so that the interactions, even at temperature 0, can actually populate these fluctuations. We are ignoring these, and so this is true only when the interactions are essentially weak, or at least the diluteness condition is satisfied. Okay. So in this limit, the next thing we wanted to understand is this is describing the dynamics of the condensate wave function. But then we can ask the question, given some external potential and some interaction between the atoms given by this equation, what is the ground state, or what is the steady state that this condensate wave function is going to be in? After all, when you make a Bose-Einstein condensate in these experiments in a trap, you would imagine that you would make the condensate into the ground state or the lowest energy state. In order to do that, we developed a time-independent version of this Gross-Pitaevskii equation. The idea there was to start with this many-body wave function and calculate the expectation value of the many-body Hamiltonian in this trial wave function, and then do, and this average H gives us this object called the energy functional, and this energy functional represents the energy of the condensate as a function of the condensate wave function. And once you do a variational principle on this energy functional, you end up with the equation that is precise with the constraint that the condensate has n atoms. The normalization condition, when you minimize E of psi with this normalization condition as a constraint using this Lagrange multiplier, which is given by the chemical potential, you end up with basically the time-independent version of the Gross-Pitaevskii equation. So these are the two central equations that we are going to study today, and study the properties of and interesting implications of this. So one thing I promised at the end of yesterday was we will try and understand physically a little bit, why does this chemical potential, can we justify how the chemical potential enters this time-independent GPE? Because the reason why I'm asking for a justification here is, if you remember your basic quantum mechanics, the eigenvalue equation, you would expect the energy to appear, but it's actually the chemical potential that appears, because this is actually a slightly different object. This psi of r is not the wave function of a single particle, but it's like an order parameter that represents the wave function or a wave-like property, the density matter wave of a Bose-Einstein condensate. So that differences are there. And let's see how mu enters this equation physically, okay? In order to do that, I want to just point out how we could have derived this equation in a slightly different manner. This is a dynamical equation. If I want the steady state solution or a static solution of it, just as I would do with the Schrodinger equation, I would just assume psi of RT is equal to some e to the minus I mu t over h bar psi of r, right? I can do that. That's very simple. So once I do that, I will directly get this equation immediately, right? So if I assume that the time evolution of my condensate wave function for the stationary, when in the stationary scenario, when my condensate wave function doesn't evolve except for a phase. So basically, if my condensate is in the ground state of my is in its ground state, then I am saying that my time evolution has to be given by the chemical potential. Can we justify this? Why is this the case? Because that has to be the case, and that is why we are getting this time independent GPE with the chemical potential as the non-linear eigenvalue, so to speak. Okay, so now let's see why is this happening. So one way to understand this is to start with this Bogoliubov ansatz, right? So because at the end of the day, everything that we do, we started with this Bogoliubov ansatz, where we replaced an operator corresponding to the atomic field by actually a complex function, right? So that is the replacement that the Bogoliubov picture is doing to us, the mean field picture. One way to think of such an replacement is to think of this psi of RT as basically the average of psi of RT, the field operator. So you can think of this condensate wave function as the average of the field operator, okay? So this is precisely what we did when we said that we are replacing A0 by essentially square root n0 yesterday. And this is like saying that A0 is like square root n0. This should be a little bit familiar if you have some background in quantum optics, where, for example, if I have a annihilation creation operator for a harmonic oscillator, and if I have a coherent state, then I can replace, in some sense, if when the number of photons corresponding to this is much larger than 1, I can replace the operator A by basically the complex coherent parameter alpha. And remember that the complex coherent parameter is actually just the expectation value of A. This is how mean field theories work, basically, in quantum mechanics. Okay, so with that in mind, we can imagine that this order parameter, the condensate wave function, is just the average of the bosonic field operator. But there is a problem here, because if this is a regular kind of expectation value, we'll take expectation value with respect to the n particle state corresponding to the condensate, right? But now, if I basically put in two n particle energy eigenstates of my system and sandwich my field operator in between, what happens to this? This has to be 0, right? Because see, this guy is going to annihilate one particle at the position r. So this is going to give you an n-1 particle state. And of course, this is going to be 0. Okay. Now, the problem is what we can. So this precisely tells us that we cannot really sandwich on both sides with an n particle state, right? So the idea then is to really sandwich with an n particle state, an n-1 particle state on the left and an n particle state on the right. Okay, and that is the expectation value that will equal the psi of RT. Okay, so now if you put the field time dependence onto these energy eigenstates instead of the field operator, which we can do because expectation values doesn't matter which picture you are in, Heisenberg or Schrodinger. Now this object, psi of n, evolves as e to the minus I energy of the n particle state. Psi of n-1 evolves as e to the minus I e of n minus 1 T by h bar, right? So let me just check if I talked about this yesterday, because I thought that I did not. Yes, I did not. Okay, good that I'm talking about it now, because I had a little bit of a deja vu and I was wondering if I was repeating myself. Okay, so if I have this kind of a situation and I sandwich this, it becomes clear that this object, our psi of RT, precisely evolves as e to the minus I, e of n minus e of n minus 1 T over h bar. But this is precisely the change in energy per particle as you add, and which is essentially dE by dN, which is precisely the chemical potential, right? So this justifies why when we find the stationary solutions of our GPE, we write it in this manner, with the time evolution given by the chemical potential, but not the energy of the n particle state. Okay, so that's just a justification I thought I would give for the time dependent and the time equation. Sorry, Gross-Pitaevskii equation. And now with this settled, we can actually study different properties of these Gross-Pitaevskii equations. So let's first begin with the stationary or the time-independent Gross-Pitaevskii equation and study some of the interesting predictions and some of the interesting properties that arise from this equation. Okay, so let's begin with the simplest case there is. So let's take the time-independent Gross-Pitaevskii equation. Let's first consider the simplest situation. Okay, the simplest situation you can think of is basically an uniform BEC, right? In which case I will take basically V of R, the external applied potential 0. Moreover, my steady state is, because it's a uniform system, my steady state gradient is going to be 0. So this kinetic energy term just vanishes. So what am I left with? My equation just becomes U0 psi 0 of R. There is no R dependence, so it is just psi 0 squared. Psi 0 is mu psi 0. Now this tells me, cancelling the psi 0, that mu is precisely equal to U0 times psi 0 squared. Recall that for a normalized uniform solution, psi 0 is just 1 over square root V, right? Times square root n. So an uniform wave function is, if in some volume V, is just 1 over square root V, right? This is a wave of wavelength infinity, essentially. So then psi 0, which is square root n times pi of R, that is square root n over V. So we get the result that the chemical potential is just U0 times the density for a uniform BEC. This makes complete sense, right? Because all that we are saying is that when you have a uniform BC, there is no kinetic energy, there is no potential energy, there is only interaction energy, and the chemical potential to add one more, which is the energy required to add one more particle, is precisely just the mean density times the interaction energy U0. So it is just the interaction energy per particle that gives the chemical potential. Okay, so that's the simplest prediction from the GPE, which is agrees with our intuition. Okay. Now let's go to the more interesting and more relevant thing. For actually, no one has made a completely in a completely uniform system. It is not a BEC. Very simply, has not been made. Of course, you've made some box traps now, but what is usually done is we are interested in Bose-Einstein condensate in traps, right? So we are interested in potentials of this form, and we want to understand what are the prediction of the Gross-Pitaevskii equation for the ground state of Bose-Einstein condensates in such traps, right? So now, of course, this is not a hard problem. This is a very simple equation, right? This is just some simple differential equation. And given an external potential, and given some value that it takes, I can measure the scattering length of these atomic interactions. One can actually just solve this equation numerically, and it's actually quite a big sort of subfield in itself of trying to understand the mathematical properties and how to numerically efficiently solve this Gross-Pitaevskii equation. But we are not interested in that in this course. We want to actually develop a little bit of approximate analytical intuition for what should be the solutions when we have such a Bose-Einstein condensate in a trap. So let's begin with a qualitative picture. What should be the what should we expect? Okay, so qualitatively, if I begin, instead of considering this anisotropic trap, let me just consider an isotropic trap with some half m omega squared 0 squared r squared, right? So all the frequencies along the three directions are the same. In this case, my let's say that the spatial extent of my Bose-Einstein condensate is some r, capital R. Now I want to qualitatively estimate how big my condensate is based on this Gross-Pitaevskii equation, right? So let me begin in the limit where my interactions are not so important. Then from this or from my energy functional, let me just take this guy also over just so that you can see it, right? Okay, from looking at the time independent, sorry, this is really bad. This is time independent GP that we are considering. So looking at just this, we can actually estimate roughly what is the potential energy and what is the kinetic energy for a cloud of size r. So potential energy is simple. It is just of the order of half m omega 0 squared r squared, right, for a cloud of size r. So now for the kinetic energy, this is again easy. It is just if the cloud size is r, its wavelength is of the order of 1 over r. So it basically becomes h bar squared, h bar by 2m r squared, right? So this is something we can easily work out. This is the kinetic energy. Okay. So now with this, what can we do? So we can actually ask if the interaction energy can be completely ignored. We can ask what is the optimal R by trying to minimize this potential and kinetic energy as a function of R. Okay, this is a very simple minimization of two terms with dependent on R. And then what happens is basically the optimal or the right radius of my cloud is basically when the potential energy and kinetic energy are comparable. When I do that, I basically get that R is essentially of the order of h bar by m omega to the half, which is just the oscillator length of my harmonic oscillator. In other words, all that I have sort of indicated here is just the variational calculation of the ground state of a harmonic oscillator. That works as long as my interaction is small, right? So that basically, this is the idea that I used in the beginning, like a couple of lectures ago, where I said, well, the ground state of the condensate is just going to be, if the interactions are small, it's just going to be the ground state of my harmonic oscillator. Okay. But now, of course, we have much more than that. So now we have interaction. So if the interaction strength starts, so when it matters, so if you add interactions, what happens? Basically, you can estimate what is the strength of this interactions, right? So it is basically going to scale when the density is basically just the number, the interaction. Let's estimate what is the interaction strength in a cloud of radius r or size r. So the density is just going to scale as n, the total number of atoms over r cube, right? So now the interaction energy per particle in this situation is precisely just n times u0, like we estimated last for the uniform case. It is, as an estimate, this works. This is not exactly how it is because the density actually changes in space and so on once you have a potential. But for an estimate, this is good enough. So this is just nu0 by r cube. Okay. So this tells us that adding interactions gives an energy that goes as r to the minus 3. So if you want to find the ground state and keep the interaction strength small, the system would prefer to make R larger, right? And this is not crazy, right? So it is basically, if I have interactions and I'm interested, sorry, now I should be very clear that I'm interested in having repulsive interactions. Okay, so if the interactions are repulsive, my cloud size is going to increase, and my system would want to make a larger cloud. Okay, so now what happens then is that typically in any Bose-Einstein condensate experiment, the radius of my cloud is going to be larger than definitely this oscillator length, which works only if you have no interactions. So now, if I go to this stronger and stronger interaction limit, right, then R is going to become larger and larger. Remember that my kinetic energy estimate goes down as 1 over R squared, right? So when that happens, if the kinetic energy estimate is going as 1 over R squared, if I go to larger cloud size and stronger interaction, my kinetic energy is going to go to 0 very quickly. So in this limit, in order to find my optimal radius of my cloud, all that I have to do is I have to equate my interaction energy to my potential energy, right? So I'm just going to minimize the sum of the interaction and potential energy, and that is minimized at an optimal R that satisfies this equation, right? So when I do this, after a little bit of algebra, one sees that R basically goes as R to the phi goes as n u0 by m omega 0 squared, and you plug in for u as 4 pi h bar squared a by m. And after a little bit of algebra, one can show that R is precisely a oscillator and a over a oscillator whole to the 1 by 5. So this NA over a oscillator is a very nice measure of the interaction strength, right? For typical experiments that have been done with ultra cold atoms, Na over a oscillator. So basically the scattering length of these alkali atoms is of the order of some nanometers. It's very tiny. And the A oscillator is typically for these hundreds of hertz or typically 1 kilohertz order traps. It is of 1 micron, and n is typically 10 to the 4 to 10 to the 6. In this limit, you end up with R over a oscillator a few times 1. So I was sort of not being very correct when I was explaining this famous Bose-Einstein condensate picture, saying that, well, the extent of the cloud is just the oscillator length, right? So it is actually not the oscillator length. Because of the interaction, the cloud is a little bit larger, okay? But this can be estimated, and this has also been verified in experiments that you can see such an expansion of the condensate. Okay, good. So this is very, very qualitative. Now let's get a little bit more quantitative. There are two quantitative ways in order to essentially find out what is the exact psi when you have a trap. Okay, so the first one is really a more formal version of this variational calculation, right? So one thing I did not mention here is basically what happens if U0 is less than 0. We will come to this in a moment in this next step. But when U0 is less than 0, what happens is that as long as your interaction, it is very similar to the, in some sense, to the non-interacting case. But what happens is basically because of the attractive interactions, your clouds are going to be compressed a little bit. But there is another interesting point, which is your interaction energy that tends to favor all of the atoms and the clouds to collapse has to be balanced by the kinetic energy in the trap, which is given by the fact that in the trap's wave function has some Gaussian shape, right? If it were a flat shape, if it were a uniform situation, if I have attractive interactions, I will basically collapse my condensate. Basically, all the atoms being at one point is the ground state. So I will not have a Bose-Einstein condensate, which is uniform and attractive interactions. But having a trap allows me to have a wave function with some kinetic energy that sort of gives me a balance, because if I have a free sort of a Gaussian wave function, you know that there is always a tendency for it to spread. This spreading tendency, which comes from having kinetic energy, that balances against the attractive interactions. Okay. So now, but that can happen only as long as the number of atoms is below some threshold, given other things are kept constant. If you have a particular scattering length, particular oscillator length, there is a critical NC up to which you can still have a condensate, but below that you will basically collapse. Okay, so that's what will happen with the attractive condensates. We will not discuss too much about attractive condensates, but we will see in a moment a small idea that you will get of. We'll get a better idea of what I just said. So the first quantitative method is basically, as I said, a formalization of the variational calculation. So I can start with this proper three-dimensional oscillator, and inspired by the ground state of this oscillator, I will actually simply do a variational calculation, right? I'm just going to take my psi of r to be precisely of a Gaussian form, but the Gaussian widths, the width of the Gaussian is no longer the harmonic oscillator length, because we just saw that that is not going to work once you have interaction. So the next nearest best thing is to still assume it's a Gaussian, but keep these widths free. And I can take this and plug it into this energy functional, and this now becomes a simple function of these widths. And then I can look for the minimum by extremizing this energy function, right? Then that will be the wave function that will satisfy my stationary GP, and that will be the ground state. So when one does that, let me get rid of these things, sorry. When one does that, we see this very nice behavior, right? So what happens is basically, if I do this and consider the situation where I have, instead of an anisotropic case, let me think the simplest case. With isotropic, there is only one B. In that case, if I plot the mean, the energy functional as a function of this width of my Gaussian, one sees that as long as I have repulsive interactions, so NA by A oscillator greater than 0, there is always some minima that I can find. Okay, and that will be basically my the solution to my stationary GPE according to this variational principle. But now, if you look at the negative interaction or the attract negative case, one sees that initially when n magnitude A by A oscillation is of the order of this minus 0.3 here, you see that there is a minima. But as you keep increasing this NA by A oscillator beyond essentially this NA by A oscillator of the order of 1, when the interactions win, what happens is basically you no longer have this variational minima, and you cannot have an attractive condensate. So in fact, from here to here, you can simply go by increasing n, right? So if I keep increasing n, eventually my variational calculation will fail in this case. And this is telling me that I cannot have a condensate in the attractive case beyond a certain critical NC, which is, you can estimate it by saying NC magnitude of A by A oscillation of the order of 1. Okay, and the cloud will collapse if n is greater than this n critical. Okay, so this is one way to do the calculation, but this is again in the limit where I am only considering I'm still sort of sticking to my I'm coming in from the non-interacting side, right? So because I'm assuming that I have a Gaussian, which if my interactions are 0, my BI all go to AI. So now I want to go completely away from it, and I want to understand how does the wave function look when interaction completely dominates the physics. In this limit, when interactions completely dominate over basically the kinetic energy of my system, because remember, interactions, I'm just now interested in repulsive case, interactions are just going to make my cloud larger, and means my density patterns in the cloud are all of very long wavelength, so the kinetic energy is really small. So in this limit, I can actually find an approximate solution to my ground state of my GPE by completely ignoring the kinetic energy. So I can completely ignore this object and just solve this equation, right? So if I did that, if I start with just this is very easy to solve, right? Because this is just psi will cancel, and I basically get that my density n of r, which is just absolute value of psi of r squared. So n of r, if I just get rid of this psi of r and write it in terms of mu, n of r is precisely given by mu minus v of r over u0. Okay, so this solution is called the Thomas Fermi approximation. And all that we are saying is that in this limit, my density precisely has the inverse shape of my oscillator. My oscillator is like this. My density distribution is precisely minus of V of R. Okay, that is the shape. But of course, there is a certain issue here. This cannot be true for all R. So what happens? We need n of R should be greater than or equal to 0. So the correct Thomas Fermi solution is that the wave function, the density, in fact, is mu minus V of R by u0 as long as my potential is less than mu. And it is 0 as soon as V of R greater than mu. And I can determine mu from the condition that integral d3r n of r should be n. This will determine the chemical potential for me. So at the end of the day, my cloud, I can really find the shape of my cloud by simply writing this V of R equal to mu, right? And because this V of R is of this quadratic form, this is precisely the equation of an ellipse. So my cloud, let's say my extent of my cloud. So the point where my V of R equals mu, that gives the extent of my cloud. Beyond that R, beyond that radius, there is no atoms. So in this limit, I can basically write this as half m omega squared rx squared, omega x squared, half m omega y squared, ry squared, plus half m omega z squared, rz squared equal to mu. And this is the equation that is satisfied by my Thomas Fermi density distribution. And I can just work out what these Rx, Ry, Rz are in terms of the chemical potential. So Ri squared is precisely the radius of my cloud along the ith direction. It is just 2 mu over m omega I squared. And I can use this and calculate integral dtr of n. And from that, I can actually estimate that my chemical potential is precisely going to go with some numerical factors as NA over this A oscillator length. So this is the mean oscillator length where omega, this is A bar is just H bar by M omega bar to the half. Omega bar is the geometric mean frequency of this trap. Okay, so this gives me the chemical potential. And this is basically the Thomas Fermi calculation that tells you how does the cloud look in the limit when my interactions are very large. So this is again a very, very nice and nice sort of probe to show that really one has a BEC, because any thermal gas would never have such a profile. For example, in this Thomas Fermi case, you basically have a density distribution that is simply just the inverted version of your potential. As you, since you can control the interaction in these systems, you can go to really strong interaction with, if you have a larger, and if you make, for example, the effective interaction strength is larger when you add more atoms. And then for a very large atomic cloud that makes a BEC, it's very beautifully seen in many experiments that really you end up with this very nice Thomas Fermi profile, which cannot happen if you did not have a BEC. Okay? So that's sort of all that I wanted to say. There's just one more small thing, but regarding the stationary solutions. Before I go there, I want to stop and take some questions. If you want, you can switch on your mic and ask the question. Meanwhile, I'm just reading the chat questions. So There's a question from Raghav which says, instead of applying the variational principle to the energy functional, can we use the least action principle to obtain the time independent NLSE? So typically, if you use the least action principle, you end up with a dynamical equation. So there is a very simple way to define an action for this Gross-Pitaevskii type situation, and you can get the time dependent Gross-Pitaevskii equation from the action, but I'm not sure if you can get the time independent equation from that. Then is the harmonic trap produced using magnetic field? Yes. So typically these harmonic traps are magnetic ones, but you can also make optical dipole traps where you can use the optical dipole force. So in a harmonic oscillator, we know that the wave function is non-zero even outside the length of the oscillator. So don't we need to consider this here? I am not sure what that question is, because in that case, all that is happening is I'm taking a Gaussian. Of course, beyond the oscillator length, also the Gaussian extent is there. But the idea is that most of your density is within this region. That is the idea. Yeah. So I don't know if that makes sense. All right. Any other questions? Okay. If there are no immediate questions, let me proceed. The last sort of property that I want to consider from the stationary or time independent GPE is this idea of healing length that someone actually mentioned previously. So what is this healing length? So in order to understand this healing length, I'm interested in a situation where basically I have considered very smooth harmonic oscillator type potentials for the condensate so far, right? So now imagine that I have a slightly more harsh situation, or a more sort of potential that is very abrupt, which is a way to mimic, for example, a localized disturbance that I can make on this condensate. So consider a potential of the following form. I have basically potential, a kind of a box type potential, right? So I have for x less than 0, I have v is infinite, and for x greater than 0, from x greater than 0, v is 0, right? Now, my condensate is living in this sort of a potential. Of course, you can ask, what about the other dimensions? So it turns out that you can actually consider one-dimensional versions of the Gross-Pitaevskii equation for a very simple reason. The idea is, if I take in a real experimental system, this is relevant because I can take my harmonic oscillator trap and I can make two of these frequencies very large, right? When I do that, or let's say omega y and omega z much greater than omega x. So when I do that, the harmonic oscillator length or the confinement in the y and the z directions becomes really tiny, and I get a very elongated condensate or an elongated shape for my Bose condensed cloud. And in some sense, whenever I'm talking about a one-dimensional version of Gross-Pitaevskii equation, I'm precisely talking about this condensate in such a cigar-shaped condensate, but in the limit where I'm really talking about the bulk, where I do not see the edges. So in the middle of the cylinder, really I have effectively an one-dimensional system, okay? And by making this width, by making omega z, omega y slightly, smaller, I can also get very many. I can get an effective 2D situation. For example, a cylinder kind of a situation, which is why it's called a cylindrical trap. And I'll consider such a configuration later as well. So the basic idea is that I can play with this trapping frequencies and essentially consider I can make one-dimensional, two-dimensional, three-dimensional system. I have complete control in these Bose-Einstein Condensates systems over the dimensionality of my gas. So that is why considering even one-dimensional effective models when we are talking about the GP equation makes sense. It's not some science fiction. with that sort of background, let's ask what happens in this case where there is no potential in the in anywhere to the right. So this is V of X, right? And from here on this side, it is completely infinite. Okay. So of course, in the bulk, because this is essentially a uniform system, I would expect my condensate to be go to some constant density n, right? That is something I expect. On the other hand, I would expect that because of the fact that this is an infinite potential, and this is again like a wave equation, right? So my Gross-Pitaevskii equation is a wave equation. I would anticipate that my psi goes to 0 at x equal to 0. So now the whole question is, how long does the system, does the Bose-Einstein condensate, over what length scales does the Bose-Einstein condensate forget the boundary? Or in other words, for how long does a boundary effect last within the Bose-Einstein condensate? This length scale is called the healing length. And this length scale sometimes is also called the coherence length. And its meaning as coherence length will also become a little bit clearer when you consider the fluctuations of the GPE. But the basic idea is, as you go closer and closer, there is no to the wall, there is no condensate, and basically the condensate sort of recovers in the bulk. So now the idea is we want to estimate first this psi, and then write down, for example, what should be this wave function in such a situation. Both of these things are important for us, and let's just do that now. Okay. In order to estimate this, all that we want to do is following. So away from this wall, there is basically so as you move away from the wall, what is happening is now you have essentially the density distribution n of r, or n of x, is now position dependent here. Or in other words, there is actually kinetic energy available to the condensate here, right? So when you are completely flat, the kinetic energy, so if you look at kinetic energy locally, there is zero kinetic energy here, but as you get towards the wall, your density distribution is changing shape, right? It is going to 0. There is a gradient of the magnitude of psi, and as a result, I have kinetic energy. And now the length scale over this, which this change happens, is precisely governed by the competition between the kinetic energy, so this is a perturbation of this length scale psi. So the kinetic energy of this is precisely h bar squared by 2m psi squared, right? Now, this kinetic energy, the size of this psi is precisely set by the competition between this kinetic energy and the interaction energy. There is nothing else here. There is no potential in this region, right? So the potential is completely 0. So now the interaction energy scale is precisely nu0. So by equating this kinetic energy and the interaction energy scales, right, we can estimate this healing length psi. So this psi is precisely given by h bar squared by 2m nu0. And you can also think of it as basically, you can write this u0 in terms of the scattering length, and that will lead to 1 over 8 pi n a, where n is the density. So n here is the density in the bulk. Okay, this is the density at once you go far away in the x tends to infinity limit, and this is n times a. So now this 1 over n, remember, is like interparticle separation, and this is basically, you can think of this as the interparticle separation cube over the scattering length. That is precisely what this healing length square is. Sorry, this is the healing length square. So the healing length is actually square root of this object. The healing length is h bar over square root 2n. Okay. And it basically tells us what is the length scale over which the condensate comes back to its bulk density. Okay. So with that, we can also we can also do this more quantitatively. If you solve the Gross-Pitaevskii equation with this boundary condition that psi of x equal to 0 is 0, psi of x tends to infinity is basically n0, and there is no potential. If you solve the Gross-Pitaevskii equation with these boundary conditions, the time independent Gross-Pitaevskii equation, you precisely get the wave function corresponding to this healing of the condensate. And that is actually just, as I was trying to draw, I didn't draw it so well. It's actually like a tan H function. Okay, so psi of x is precisely psi 0 tan hyperbolic, and you can show clearly that in that case, this solution works, and this healing length will appear. Whatever you have taken as this healing length qualitatively will appear in the exact solution of the Gross-Pitaevskii equation corresponding to these boundary conditions. Okay, so that's the last thing I wanted to say about stationary solutions of the Gross-Pitaevskii equation. Now let's go to the dynamical version of the GPE and look at some interesting properties. Okay, so now the dynamical equation is precisely this. So let me actually speed up things a bit. Instead of me writing down things repeatedly, let me copy a few things. Okay, so what I can do now is I can start with the dynamical equation, take its complex conjugate. Okay, so now I have pair of equations, and I can now, I'm interested now in taking my Gross-Pitaevskii order parameter and writing it as some densities square root, which I can do always, times some phase function. Okay, and so this phase function is of this form, right? Or some function f of rt that is real times a phase. Okay, f and square root n are interchangeable. Okay, and now I am looking to develop essentially an equation for the density and the phase. Okay, and the language, it will become quickly clear because I'm going to talk about the density of this, and we will see a velocity field will come up. As a result of these things, all of this approach that I'm going to use, this is sometimes the first thing we want to consider with the dynamics of the GPE is this so-called hydrodynamic description. So I'm going to treat this order parameter and the BEC like a fluid and develop a set of equations describing the fluid density and the fluid velocity flow. And that is a very nice analogy to understand the Bose-Einstein condensate as really like a fluid. Okay, good. So with that, if I just basically take psi star times this equation and psi times this equation and subtract, I can immediately get an equation for the density d by dt of absolute value of psi squared, which very simply becomes this, right? Now, if I identify from here, this is basically my density, right? And I identify what is inside here as basically the density times velocity. This equation dn of rt by dt plus divergence of n times v equal to 0 precisely has the form of a continuity equation of a fluid. Okay, this is not very surprising because you see the Gross-Pitaevskii equation has a form very similar to the Schrodinger equation, and this is something that you must have seen when you took the Schrodinger equation, and you would have written such an equation, and you would have written such an equation for the probability density psi of rt squared, right? Now, the interesting thing is I am writing this equation for not the probability density, but it's actually the order parameter squared. So this is really describing the density of the Bose-Einstein condensate fluid. Because there is a popular misconception when you try and develop the hydrodynamic equation for corresponding to the Schrodinger equation. There, the fluid is actually not a real fluid. It's actually the probability density that flows. There is no mass transport, so to speak. But here, what I'm talking about is a real fluid. Okay, so there is, because this n really depends on the number of atoms. It is n of RT is n times the wave function phi of RT or wave function squared, right? So it is really talking about the mass transport or the continuity equation corresponding to the fluid that is my Bose-Einstein condensate. Okay, so if I'm identifying this inside thing as n times V, my V is precisely nothing but h bar by 2I psi star grad psi minus psi grad psi star divided by absolute value of psi squared, right? Because I have to divide and multiply by absolute value of psi squared to write it as n times V. So once we do that, we can immediately see if we plug in this phase and amplitude description, this velocity, which sometimes we will call it as superfluid velocity or V, is precisely nothing but h bar over m times gradient of phi of RT. Okay, so this really gives us the idea that the velocity field corresponding to the Bose-Einstein condensate is precisely set by the phase. Okay, and this also tells us something else that is a little bit interesting. That is that when you have a stationary solution of your GPE, the ground state, typically the solution is always real. Okay, so there is no, so the gradient of the phase is 0, and that makes sense because in the stationary state, I would not expect some flow of my condensate. Okay, so this V is actually related. You can treat this Bose-Einstein condensate as a superfluid. I won't go into a lot of details of that. We'll see a little bit of the features, but this is basically telling us that the velocity field is precisely the gradient of the phase of my condensate wave function. Okay, so this is one part of the equation, but now I can also write an equation for basically this velocity field. This is somewhat easier to do. So what I'm going to do is I'm trying to break up this equation for psi of RT into two equations because there is a real and imaginary part. So the continuity equation has given you one equation. After a little bit of algebra, you can write an equation corresponding to the velocity field. Okay. So instead of subtracting, you just multiply. Instead of subtracting, you just add. You'll get additional equation, right? So then that equation, which is very suggestive in terms of this hydrodynamics, that equation has the following form. This is the V external of RT. So this equation is actually very similar looking to the Euler equation that one writes for fluids. Okay. And the role of this, so here this pressure is basically the pressure that is coming from having the interactions. Okay. So this is the pressure really for a uniform BEC. And I mean, you can work out what this pressure is by realizing that if I'm at temperature 0 from the Gibbs-Duhem relation, my change in pressure is just n times d mu, where n is some density. So this is my local density. So this is like the local pressure P of RT if you want. So this is n d mu. And now with this mu, if I'm in the limit where I can essentially locally have some constant density, I can still write my mu as some n times u0, right? Which means I can write my dp as basically u0 n dn, and p is precisely u0 n squared by 2. So in reality, when you write down the equation, I got u0 n squared by 2 here inside the gradient. I'm just justifying that I can identify this u0 n squared by 2 precisely as the pressure due to having interactions in my system. Interestingly, one can see that similar to this, I have an additional term here. Okay, this additional term, when you write even your Schrodinger equation in terms of this hydrodynamic description, this term will be present. This term, you can see, precisely comes from the fact that my n of RT is non-uniform, right? So it means it comes from having gradients in density or it precisely comes from having kinetic energy in my system. And this sometimes is called, because it has this, it occurs in the same form as the gradient of pressure in an Euler equation. Sometimes this term is called the quantum pressure. And hopefully you'll have time today. We'll see that there can be competition between this quantum pressure and the real pressure that comes from the interactions. And you can balance the two to create very interesting solutions of the Gross-Pitaevskii equation, which are called solitons. Okay. So we will see that very soon. Okay. So this is all I wanted to say about the hydrodynamic description. And before I move on, are there any quick questions? Okay. If not, let me move on to the next thing I want to do, which is to consider. So far, we have only considered the stationary solutions of the Gross-Pitaevskii equations. We want to basically perturb about such stationary solutions of the Gross-Pitaevskii equation and look at the behavior of the small perturbations and understand what elementary excitations of the Gross-Pitaevskii equation, fluctuations about the ground state, how does it look? So we want to take the following form of solution to my time-dependent Gross-Pitaevskii equation, which is precisely something like square root n of r e to the minus I mu t over h bar. This is basically my ground state solution plus some fluctuation delta psi of r. Okay, and I want to plug this into basically the Gross-Pitaevskii equation and its complex conjugate. Okay, because in principle, I have these are two independent equations I have. So this is just mathematics, so one can plug that in. Okay, so I'm just going to now be a little bit quicker. Go to the physics quickly. Okay, so this is my this is what happens when I plug in such an ansatz into my Gross-Pitaevskii equation and its complex conjugate, and I ignore delta psi squared, right? Because I have an u mod psi squared term. If I plug in this, I will also have delta psi squared terms. I am going to ignore those terms. Why am I doing that? That is basically because I'm assuming these are small fluctuations and I am essentially linearizing the Gross-Pitaevskii equation, which is actually a nonlinear equation. Okay, and this is my situation. Now I am interested in periodic excitations of my system of the following form. And I want to understand what is the energy of corresponding to such periodic excitation, which is all this elementary excitations are about. I will take them of this form, e to the minus I mu t, u of r, e to the minus I omega t, minus v star of r, e to the I omega t. Okay. And I'm adding this additional e to the minus I mu t over h bar because I want this elementary delta psi of RT, this equation, when I plug it in, I want to cancel this chemical potential time evolution. So that this, whatever I write, the equation I write for u and v from here, that equation can be satisfied for all time. Okay, so I'm going to develop from here an eigenvalue equation for my excitations u and v. Okay, so once I do that, this is very simple. This equation is precisely this. Okay, so these equations, by plugging in this form of my fluctuation, I get an equation for u and v. These equations are called Bogel-Lyubov equations, and they describe fluctuations about an steady state of my Gross-Pitaevskii equation. For example, these equations are extremely important, and I have written them for a generic potential and interaction, right? So now these equations are extremely important when you have like complex potentials like lattices and so on. What good are they? So when you look at this equation and calculate this omega as the eigenvalue, what is the eigenvalue of omega that you get? As long as this, in principle, these eigenvalues can be complex, and complex eigenvalues, if you get a complex eigenvalue, it tells you that the original solution about which you're perturbing actually is not stable. Okay, so this is very useful in analyzing the stability of solutions of Gross-Pitaevskii equation. That is one very important practical use of this for general potential cases. But we are now going to take this equation and consider the simplest situation there is and understand the properties of elementary excitations of a uniform Bose-Einstein condensate. So we will take V of R equal to 0. So the solution we perturb about is going to be just a constant potential, right? So sorry, N of R is equal to N0. Okay, so we're going to perturb about such a constant solution and in a uniform potential. So V of R we take 0 and N of R equal to N or N0. And now we want to understand what U and V is. Okay, so then this equation becomes even simpler. So we take the following situation. Okay, so now we are taking a uniform case and we are interested in, since this is uniform, since this is a uniform system, the excitations are going to be some plane waves, right? So we take excitations of this plane wave form with different wave numbers, Q, okay? And once you do that, in this equation, you take V of R 0 and take U of R is UQ e to the IQ dot R, you end up with this very nice matrix equation for the coefficients UQ and VQ. So this is of the form M UQ VQ equal to 0. Okay. Now, for this equation to have a non-trivial solution for UQ and VQ, this matrix, determinant of matrix has to be 0, right? Or in other words, I can solve this eigenvalue equation for omega. And after a little bit of algebra, I basically get the spectrum of my elementary excitations very nicely as h bar omega squared equals EQ0, EQ0 plus 2NQ0, okay? Where EQ0 is the energy of a single particle in some sense with momentum Q, which is the excitation wave number, okay? So now I can even write this, the positive solution to this equation, which is the thing that represents my excitations or my fluctuations, can be written in this manner. Okay, so this is called the Bogoliubov dispersion relation for the excitations of a Bose-Einstein condensate. Okay, so now let's analyze this dispersion in two limits, right? So if I am in this limit where my interactions are if I'm in the limit where my wavelength Q is so large, so my wave number is very small, right? And my wavelength is very large, so long wavelength excitations. Then my EQ0, my kinetic energy, this is going to be much less than 2NU0. Okay, so then my omega actually becomes 1 over h bar square root. I can write this as EQ0 plus 2N0 as basically 2NU0 becomes EQ0 2NU0. After a little bit of algebra, this just becomes, because EQ0 is Q squared, this just becomes precisely of the form Vs times Q. Okay, this Vs, so this sort of dispersion is what's called a phonon dispersion. And this really is talking about an excitation of my Bose-Einstein condensate, which is uniform, an excitation that is a sound wave. Okay, and the velocity of this excitation, which is the sound wave, is precisely just given by NU0 over N. So it is set by the interactions in my system. Okay, so this is a long wavelength excitation. So many atoms are participating. So in that sense, it's a collective excitation of my Bose-Einstein condensate. Okay, and that has this phonon-like form. On the other hand, if I am in this other extreme where my kinetic energy is extremely large, and so I am in a case where my wavelength of my excitation is really small and wave number is much larger, in this limit, I can basically take this dispersion, right? And I can write EQ, which is h bar omega, and I can expand this basically as EQ0. I can pull out an EQ0 squared out and take 1 plus 2 NU0 by EQ0 squared whole raised to the half. And then I can expand this. I can write this as EQ0, 1 plus NU0 by EQ0 squared. And finally, I get the result that EQ is nothing but EQ0 plus N times U0. Okay. So this is a very different form compared to this short wavelength, long wavelength form. In the short wavelength or high energy limit, my higher energy excitations precisely look like single particles, right? So this is the excitation of a single particle of wavelength 2 pi over q. Okay. So in the high energy limit, my excitations are no longer collective and they are just single atoms in my condensate that are basically going with some energy h bar squared q squared by 2m. Okay. So high energy excitations are really free particles. This is just a free single particle. With, of course, there is a correction from the mean interaction, but they are very different from the low energy excitation. And one can totally draw the dispersion in these two, including these two regimes. One can pictorially show the dispersion in this manner. Okay, where at very low energies, I have a linear behavior, right? And then above a certain wave number, I basically go to this parabola, right? So this parabola is this EQ0 plus NU0. Okay. In the large Q limit, this solid line you can see is clearly joining this dotted line, which is EQ0 plus NU0. Now we can ask, at what Q do you translate from having long wavelength collective phonon-like excitations to this very non-collective single particle type excitations? In order to do that, we just have to find that length scale or that momentum scale by equating EQ0 to 2N0. So let's do that. So let's take EQ0 is of the order of 2NU0. When you do that, you get Q bar, that is, if I write this length scale as H bar squared Q bar squared by 2M, I can calculate this Q bar, and that comes out to be square root 2M NU naught by H bar. That is very nice. That is nothing but exactly 1 over the healing or the coherence length of the condensate. Or you can also write it in terms of the sound speed in the condensate. And this tells us, this gives us yet another way to imagine what is this coherence length telling us. So this coherence length is basically telling us the range up to which I can think of this condensate as a collective object when I start having interactions in the system. Of course, if I do not have any interaction, of course, it is very different. But with this contact interactions, my coherence length over which, basically, if I have no interactions, my coherence length basically diverges, right? So if I set U0 to 0, my coherence length is the entire condensate. Okay. Without interactions, my Bose-Einstein condensate is completely coherent over its entire size. But because of the interactions, we see that only over length scales above this coherence length psi, I can actually see collective behavior. And below this coherence or healing length, I basically have, in some sense, granularity or single particle-like behavior of the condensate. Interactions allow me to separate these two regimes. And hence, if I make an excitation of wavelength above the coherence length psi, that will mean that most of my condensate will participate. But if I create a very localized disturbance, then essentially that will kick an atom out of the condensate. Okay. So that again gives me a sense of what this coherence length is. Okay. So all of this from hydrodynamics. Okay. Now, in the last 10 to 15 minutes, I want to actually consider some special solutions. So far, what have we done? So we've looked at a generic description of the GPE for the time-dependent case. We've looked at the generic description of the GPE in terms of this hydrodynamics, and we have just looked at small fluctuations about the equilibrium state. Now, as I said, this GPE equation is by itself really fascinating, and it has certain solutions and certain properties for the full GPE equation that are very interesting. So I want to look at such solutions, two of such solutions. The first one I want to look at. So before I start that, are there any immediate questions that anyone wants to ask? Okay. If not, let me then just describe these two very nice solutions. The first solution of the GPE I'm interested in is called a soliton. Again, I'm going to consider this effective one-dimensional GPE, and you have to understand that I'm thinking of an effective one-dimensional solution. So now, what is a soliton? So a soliton is basically a localized wave or disturbance in your gas, or in this case, in this Bose-Einstein condensate, that actually propagates without change in shape or form. This is very interesting because if you consider essentially, let's now consider just uniform systems. So if I have a region in space which has no potential, and I consider my Schrodinger equation, and I start with some wave packet like a Gaussian with some velocity. If you have ever simulated this for just regular Schrodinger equation, you know that because of this fact that different momentum modes evolve at e to the minus I p squared by 2m t, and this initial Gaussian is made up of many of them, as this wave packet propagates, it also expands, right? So that is exactly what dispersion of a wave is. So a wave, like in some space without any potential, a wave always is going to disperse because of the kinetic energy it has. Okay, so this is one effect that is common to all waves, which is dispersion. So a soliton is something that is beating this dispersion. It moves, but it's not really, it's not really spreading. How can that happen? The answer lies in interactions or non-linearity that leads to interactions. Okay, so now the idea is that this nonlinear behavior that is part of this Gross-Pitaevskii equation describes the condensate, it can act against this dispersion and help you to preserve the shape of your disturbance. Such a solution is basically a soliton. Okay, so now, and just to see that both these effects are there in a Gross-Pitaevskii equation or for a Bose-Einstein condensate, we can just look at our the spectrum that we wrote down for our elementary excitations, right? So the spectrum clearly shows that you have both interactions, and hence the frequency of your different modes depend on the local density. This is the non-linearity, as well as dispersion that tells you that each omega corresponding to Q is different. That the frequency depends on the wave number in this manner. So both these features are in the GPE. And now I'm going to just present to you a solution that balances these two features very nicely. Okay, so I'm not going to be very detailed. I just want to give you a pictorial and sort of very simple way of talking about this soliton. So to that extent, let us just write down what these soliton solutions are. So the idea is I'm again going to be interested in completely just a uniform BEC with repulsive interactions. Okay, and this is my Gross-Pitaevskii equation, uniform Gross-Pitaevskii equation in one dimension, right? Now I'm going to write down the simplest sort of soliton solution that I can think of. The simplest soliton solution I can think of, we already have one half of it written down. Basically, if you remember this solution that we had for the healing length problem, and now instead of making V equal to infinity here, if I just have V equal to 0 for even x less than 0, that is precisely, sorry, I should go here. If V becomes 0 also here, that is precisely the situation that this equation stands for, which is a uniform potential free region. So that solution then will of course be again a tangent on this side as well. And this solution, if I write it down again, this is going to be psi of xt equal to psi of x, psi 0 tan hyperbolic x over square root psi. But of course, this is not such a fun solution because this is essentially a velocity 0 soliton. This is a disturbance. So you can show that this solution perfectly satisfies this equation. Okay. With psi of with this side becomes 0 and this side, you can show that this will perfectly satisfy this equation. Okay. So this is one example of a soliton solution. Its density goes to 0 at the center, and then it picks up and comes back to the bulk density, which is n0 over the coherence length xi. But this is a soliton that is not moving, so it's a zero velocity soliton. Sometimes this is called a dark soliton. I will tell you later why this is, because this is some analogy to optical nonlinear systems. This is dark because there is a density dip here. Okay. Now, one other important property of the soliton, apart from this, it's an exact solution, and we'll come to moving solitons and it will show this dispersion-less behavior. But one other property is if I look at the phase of my wave function, right? So if I write my psi of xt as again square root n of x e to the I phi of x, and I look at the phase of my soliton, phase of my solution as a function of x, what happens for this dark soliton is that the phase at basically x less than 0 is always pi, and it suddenly drops to 0 as you cross the point x equal to 0. So this is like a phase flip. There is a discontinuous phase flip at x equal to 0. You can take this solution, write it down like this, and actually calculate and see this behavior. Okay. So now this is essentially a dark soliton. Let's write down a gray soliton that actually moves, a solution that moves. Okay. This solution which was first discovered in the 70s. This is an exact solution, again, of this time-dependent GPE in a uniform system. And this solution is of this form. It is psi of xt, which is psi of x minus ut in this form. It is a function of x minus ut because it's going to be a wave or at least a moving object. And it can be written as psi 0, which is the bulk density. So at any given time, as x goes to minus infinity and x goes to plus infinity, this solution just becomes psi 0. So this is exactly like here, bulk, there is some density, which is given by absolute value psi 0 squared. And then inside here is the part that ensures this dispersion-free movement. Okay. Now, this is representing a solution that moves at the speed u, right? And Vs is the speed of sound in the bulk. So if you take this as the density and interactions are given by u0, this is the speed Vs. Okay. Now, this is always moving at a constant velocity u. So the width of this solution is basically given by the coherence length psi, but the width also depends on the velocity. Okay, so if the velocity is very large, right? So u always is less than Vs because nothing can propagate faster than the speed of sound inside this. This is like a medium, like a fluid. So u is always less than Vs. As u gets closer and closer to Vs, this becomes wider and wider. So it is not purely set by the coherence length of the condensate, but the speed at which it moves also changes the width of this shape of this soliton. Secondly, at the point where this will also be a shape that is like this, but instead of going completely to zero, it goes to some n minimum. Okay, so the minimum density here in units of the bulk density, which is n0 for this soliton, this is precisely u squared by vs squared. So if u goes to zero, then basically the n minimum goes to zero, which is precisely this solution, the dark soliton. And if u as u increases, this minimum density goes up and up and up. So then the final point is you can write down the velocity field in terms of the phase of this function. This is complex, so there is a phase. And you can really write down what is the change in phase as you go across at a given time. If you sweep x from minus infinity to plus infinity and ask how the phase changes, now the phase change will change smoothly across the density dip of the soliton. And the phase change is precisely given by minus 2 cos inverse of square root n min over n0. So again, if the minimum is 0, the phase flip will actually be a pi. But for in this case, the phase flip will be less than pi for any moving soliton. Okay, so this is the solution that's a soliton solution. Before I show you how experimentally this looks, I just thought I would also show you briefly in Mathematica, how does all the physics that I said with mathematically, I just showed analytically. I just wanted to show it very simply using a Mathematica. I'm just going to plot psi of xt in Mathematica and show you how this soliton really looks. It's actually quite remarkable. It's a very simple equation, but it is really rather remarkable. So let me just stop sharing Zoom here. And let me share on my computer. Okay, so I'm precisely taking this soliton solution. I'm taking the coherence length to be 1 and the sound speed to be 1. So now you can see this is the solution. This is basically the soliton with 0 velocity, showing the face of this soliton that has a precise jump by pi. Now this is the density at some time 0, and you see this will not evolve with time. It will just sit there. Whatever you do, it just is going to sit there. This is an unmoving soliton. Okay. Now, if you take a soliton that is moving and at time 0 and look at its phase, you can still see a phase jump. So this is the soliton. Let's take 0.2. Of course, you see now the density doesn't quite dip down. So this is basically the velocity of the soliton in units of the sound speed. And you can see that the density doesn't go down to 0 now. Moreover, the argument or the phase jump is also not total of pi. It is less than pi. So this is pi and this is 0. So the phase flip across the soliton is also smaller than pi. This is exactly what I was describing. So now let us look at the dynamics, which is actually quite nice to see. So I'm going to just plot the time dynamics of a soliton with velocity 0.1, right? So this is completely different from how a Gaussian in free space will move. Okay, so this is for velocity that is 0.1. So the density dip is almost 0. But if you look at a much faster soliton, then that of course has a lower dip, but it moves really fast. So this doesn't come quite down to 0. So very sort of, if it's still not clear how this soliton works, very hand wavy manner, what is happening essentially is the tendency of the interactions, which is because it is repulsive in the bulk, the interactions tend to push atoms into the density dip. Whereas the wave, if you think of this as like an inverse wave, it will try to cure this density dip by moving this peak down. So it will try to push out the atoms in some sense from here. So these two effects exactly compensate in this solitonic solution. Okay. And the last thing I want to show is, stop share here. And I want to show this really toy picture that I drew for you. Has very nicely been seen in an experiment with Bose-Einstein condensates. Okay, so here is basically an experiment done in 2000 where they had a Bose-Einstein condensate and they imprinted a soliton by basically imprinting a phase jump across the condensate. Because the phase and the density are connected in the Gross-Pitaevskii equation, if you change the phase of your condensate wave function, you will also change the density distribution. And with that phase change, they imprinted a soliton. And you can see very nicely as a function of time, this soliton moves down without changing the shape. So this is exact absorption images from a real experiment. And this bottom one is basically a numerical simulation of the same. So it is remarkable that this is one of the first times that a solitonic wave in a quantum system was produced in a lab. Okay, so I'll stop now and I'm happy to take questions if people have any.